And so this is an ongoing project that I've been working on with students here at Oregon State University. It's a co-funded project between AISC and PEER with the aim of being able to simulate the fire behavior of steel frame buildings in OpenSees using the latest version of OpenSees. So not using any specialty versions that you might find on GitHub. So I'll kind of give you an overview of where we are, to date, and then some new work that we've done over the last year and where we're going in the future. So just a bit of a background. I've presented at this workshop enough to know that very few of you are fire experts, and that a little bit of primer is very helpful to get everyone up to speed. So. For those practicing engineers in the audience, you're very, very familiar with the prescriptive fire protection design methods through the International Building Code. This is the traditional approach. It is very prescriptive, where you just look up what your required hourly rating is, and there's no structural analysis. You really don't have to do any calculations to determine that. That is not really where the research falls. What we're focused on is what I'm showing on the right side of the screen is the structural fire engineering. This is this is actually allowed by the International Building Code, even though some AHJs don't allow it. It is allowed by the International Building Code and considers building-specific fire hazards, and then the structural analysis of that building using temperature-dependent material properties for those building-specific fire hazards. So it's calculating what the fire would be in the building, the time temperature curve of that fire, considering the materials of the building, the occupancy, the ventilation, the size of the room, etc. So considering what's actually in the building, doing calculations, what the demand, the fire load demand on the building would be. So you can think about that's calculating the, ground motions, or the, that would be specific to that building in that area, and then performing some sort of, performing your structural analysis, determining where do you need your stronger members, where do you need more stiffness, where do you need larger members, how can you consider load redistribution so that you can prevent collapse of the building. Okay, so this is really where we're focusing on here. We're kind of throwing hourly ratings out the window, and we're using all of structural mechanics and our knowledge of structural engineering to allow buildings to maintain load-bearing capacity throughout a complete design fire. Okay, so what we've been doing so far in OpenSees is using, again, the latest version of OpenSees and temperature-dependent material properties. We first developed benchmarking examples in OpenSees to highlight the modeling capabilities of OpenSees in fire, and so that all of you on the call and anyone who's watching this video is able to use OpenSees for fire analysis. We then used those benchmarking capabilities to perform preliminary two-dimensional fire following earthquake. That's what FFE is, fire following earthquake analysis. A lot of fire following earthquake analysis shows that really there isn't a lot of significant damage due to the earthquake in your lateral system, which means that the fire performance of your lateral system is very similar to your fire following earthquake performance of your lateral system. So we really, after we performed this preliminary analysis, we wanted to be able to just kind of blanket say, at what conditions are you going to see damage? Is fire following earthquake an actual issue? And so we performed a coupled incremental dynamic analysis, incremental fire analysis on a moment resisting frame, and that's what I'll present today. The goal of all this is to really, get an understanding of how to use OpenSees for simulating large plastic deformations in a fire, performing these fire analyses so that we can actually use them to predict the behavior of buildings, steel frame buildings in a fire. So these examples, I'm just going to quickly show them on the screen. I've presented this at this workshop many times, so I'm not going to focus much on it. But these are all up on GitHub, and I'll show you the website in a second. But these examples allow users to just walk through and benchmark their modeling capabilities, starting at simulating thermal expansion, simulating beam behavior, and simulating frame behavior in a fire. The results from the OpenSees analysis were compared with analysis performed in other finite element programs more traditionally used for fire analysis, as well as experimental data. So, if you go to this link up here, you'll be able to walk through these examples and learn how to input your thermal loading. So that's what we call for these nodes, these nodal temperatures during a fire, is thermal loading. So you can input that linearly, you can input that through a temperature history from a fire itself. OpenSees does not do heat transfer analysis, so you need to get that out of another program. It'll walk you through how to simulate thermal expansion and deflections within a beam using varying restraints and varying linear or nonlinear material properties. And then lastly, it'll show you how to actually simulate a frame behavior in a fire. But again, that's not the purpose of this presentation today. Just showing you that OpenSees can do it. It's actually possible, and we used all of this modeling behavior and modeling methodologies to perform an incremental, to perform a fire following earthquake analysis. So what I previously presented in this workshop is a fire following earthquake analysis looking at 3 different compartment fires within a building. A compartment is a room or a space that has fire rated boundaries. So most of us are in rooms in our homes, or I'm in my office. So this would be a compartment, right? So these walls have certain fire ratings. And so, if there's a fire in this room, it would consume all the fuel in this room before the windows would break, and the fire would then travel to another space. And so, the goal of these compartments is to maintain the compartmentalization, okay? So you don't want the fire to travel across the floor plate. You don't want the fire to travel vertically through the building. So you don't want your floors to collapse, and you don't want your walls to fall down. So we looked at fire following earthquake in all 3 of these different compartments, and we found that this first floor compartment really had the worst behavior. We looked at different fires. We looked at fires that were short duration and long duration fires by varying the fuel load within the compartment. So we took this first compartment, and we performed a coupled incremental dynamic analysis, incremental fire analysis on this. So kind of a preliminary analysis to just see, could we bound the problem? Can we figure out, what types of ground motions would we see damage in a fire following earthquake, and what kind of fires would we see damage in a fire following earthquake? What happens if you have a high intensity earthquake followed by a low intensity fire, and then vice versa? What kinds of different damages would you see? Right. So that's what I'll present for the rest of my time here today. So again, we took this 2-dimensional moment resisting frame. We put a fire in this lower compartment down here. I realize, I'll be working in metric units throughout the rest of this presentation. Fire is quantified in degrees Celsius, so we typically use metric units. So this is a 3-story structure where you have a moment resisting frame in the east-west direction, and then you have brace frames in the north-south direction. The boxed moment resisting frame that I'm showing here is the one that we're simulating with gravity loads that are on the frame itself. So what we do is we're taking our gravity loads, putting it on the frame, subjecting the frame to ground motions, and then subjecting it to these fire loads. And the goal really is to compare the fire-only behavior of this two-dimensional moment resisting frame to this coupled incremental dynamic analysis and incremental fire analysis. So at what points does the earthquake actually make a difference at all in the damage that we're seeing within this frame? So we looked at, we took three different we took a ground motion and scaled it to three different PGAs, and we took 10 different fire curves, all representing different fuel loads and opening factors. So they're quantifying the ventilation within the compartment. And we scaled it to three different temperatures. So 30 different fire curves and three different earthquakes. And we ran all of these analyses. So for our earthquake, our scaled intensity measure, as I just showed you, was our PGA. And the way we're quantifying our damage was through story drift. And then in the fire, we used maximum fire temperature as our scaled intensity measure. And then displacement is actually quite often used to quantify damage within a building due to fire. So beam midspan displacement is what we used as our engineering demand parameter. So our ground motions, again, we took the Loma Prieta earthquake, and we looked at three different scaled PGAs. Again, this was really just like a test to see if this methodology would work. I am very aware that this is a pretty low PGA, and we, we're not surprised that we didn't really see much damage. The beams all approximately remained elastic during these ground motions. We started to see the beginnings of plasticity form in the beams during this last PGA, or this last ground motion. And then we took 10 different fire curves looking at varying opening factors and varying fuel loads within the compartment, right? So the reason we looked at opening factors and fuel loads is because a fire can either be fuel controlled. So the limit of the fire is the limit of the fuel. So the fuel is, if we look around the room behind me, we have furniture and lots of paper, I promise. So that is your fuel. So, at some point, there will be no more fuel for the fire to consume, and the fire will decay, so that we'll start going into the cooling phase. So that's a fuel-controlled fire. A ventilation-controlled fire is, there just really isn't a lot of windows. So if the room that I'm in right now had 0 windows and did not have glass on the door and everything remained closed, and you lit a fire within this room, eventually the fire would go out because there just is not air for the fire to be to consume. So then that would be a ventilation-controlled fire. And so we scaled all the fires to 3 different temperatures, and then we performed a heat transfer analysis in Abacus for all 30 of the fires for the columns and the beams that were in the compartment. Although we did not use a slab within the analysis of the moment resisting frame, we did include the slab within the heat transfer analysis because the thermal gradient through the cross section is very much going to be the control the behavior of that section and of that member. So just some results that we found. If what I'm showing you here is the interstory drift percentage in the story here. So we found that regardless of the maximum temperature of the fire, that we saw that fires with shorter heating phases resulted in a lower interstory drift, and fires with longer heating phases, we saw more movement of the structure itself.
About a minute left.
Okay, thank you. I'm almost done. The largest differences that we saw between the fire only and the fire following earthquake were for this 600 degrees Celsius, which is what we would expect. We the steel still has some capacity at 600 degrees Celsius. At 1,000 degrees Celsius, the fire itself is just destroying the structure and really controlling the damage. when we look at the maximum midspan displacement, we saw very similar results, that the behavior of the two, the fire only and the fire following earthquake, were very similar. But however, we did see that the duration of the fire played a very large role in the behavior of the structure. We saw that longer duration fires resulted in larger midspan displacements than shorter duration fires. And again, higher temperatures led to larger midspan displacements, all things that we would generally be expecting. So what's in the future? We're using this modeling methodology. We're actually benchmarking gravity framing against large-scale tests that occurred at NIST over the last number of years. So stay tuned for that. And I'm out of time, but I do want to thank Walker Matalozo, who's the graduate student who did a lot of the work that I just presented, and Michael Scott for helping us with OpenSees. And again, this research is co-funded with AISE.